We've already seen a number of situations where we looked at data and saw something interesting, perhaps a difference between two groups, and we wondered whether or not that difference is significant. In the next few lectures, we'll be developing the methodology for carrying out statistical tests in order to answer that question. Determining whether a difference is statistically significant involves answering the question, could that difference just be due to chance? Or is it so unlikely that it must say something else about the nature of the data? Let's review the inferential process again. In the real world, we have some observed data. And in the theoretical world, we have some models, statistical and scientific, that can be used to describe the real world. The statistical models include the variation that we naturally have in our observed data. The combination of our real-world data with our theoretical world models allows us to make conclusions based on our data. And how strong or how broad these conclusions can be depends on how our data were collected. Now, these conclusions could be about parameters in our models, or when our data were collected as a sample from a population, the conclusions could be about the population based on our sample. We're now going to start learning about using statistical tests in order to answer specific questions about the values of our population or theoretical world parameters. Here's how we look at it. If we observe something in our real-world data, could it just be due to chance? Or is it telling us something stronger about our theoretical world, perhaps contradicting an assumption that we've made about it? Several lectures ago, we looked at these box plots, which summarize life expectancies in two regions of the world. The box plots show that life expectancies in almost all countries in East Asia and the Pacific region are higher than life expectancies in almost every country in sub-Saharan Africa. Could this be by chance? Could it happen just because of the natural variability that there is in the measurements of life expectancy from country to country? To use statistical tests to answer this, we first devise a theoretical model that assumes that life expectancies are the same in both of these regions. And then we use our knowledge of probability and sampling distributions to see how likely it is to get the differences that we see between these two regions, or differences even more extreme. We are investigating whether our real-world data support what we're assuming or hypothesizing about the theoretical world, which is that life expectancies are the same in these two regions, or whether our data are providing some evidence that our assumptions or hypotheses are false. It may seem clear that life expectancies are not the same when comparing East Asia and the Pacific and sub-Saharan Africa. But what about this comparison between East Asia and the Pacific and South Asia? This one is less clear-cut, and we definitely need some methodology to investigate whether the differences are significant or not. Here's an example that we'll be looking at soon. In the probability lecture, Jeff flipped a beer cap that was red on one side and silver on the other 10 times, and he got 4 reds. If we assume that a beer cap, like a coin, is equally likely to come up on either side, red or silver in this case, would 4 reds be surprising? Probably not. In fact, we can't say a lot when Jeff only flipped the cap 10 times. So I had Jeff flip the beer cap a total of 1,000 times, and he got 576 reds. That's pretty close to 50-50, but if it was perfect, we would have gotten 500 reds. So assuming this beer cap is equally likely to come up red or silver, is 576, our observed data, or any value that's even further from 500, so unlikely that we think that it can't be 50-50 red or silver? If it is unlikely, we'd see what we'd call a statistically significant result. Let's quickly look at 2 more examples that we'll be examining. A recent University of Toronto study had raters examine photos of 60 patients before and after having a facial cosmetic surgery. The raters gave their guess at the age of the person in the photo, and the perceived age was calculated as the average of the raters' guesses. So for each patient, We have the difference in their perceived age from before to after the surgery. The patients, on average, looked younger after the surgery. But could that just be by chance? There's a probability distribution of possible perceived age changes. If we model it in our theoretical world as being centered at 0, in other words, we expect no perceived age change, then although some people will have positive and some people will have negative values for their perceived age change, how likely is the mean difference that the surgeons got? The other example we'll study is based on this 1992 article from the Journal of the American Medical Association. In a book published in 1868, the German Dr. Wunderlich reported on the analysis of over 1 million temperature readings from 25,000 patients, a very large data set, especially in 1868. And, ignoring fluctuations due to time of day, Wunderlich reported that 37 degrees Celsius is the mean temperature of healthy adults. This new article reports on a study to critically appraise Wunderlich's result, which stood as the standard for more than 100 years. The researchers in this article took measurements on 148 healthy men and women, and they found an average mean body temperature of 36.8 degrees Celsius. That's a little less than Wunderlich's 37 degrees. Is it a significant difference? Did Wunderlich's result need to be updated? In other words, if Wunderlich was right and his result still held when this modern study was carried out, how likely is it to get differences as large or larger than 0.2 of a degree? Wunderlich's axiom is our model for the theoretical world. Our real-world data don't completely agree, and we need to determine whether these data have a reasonable chance of occurring or whether they are giving us evidence that our theoretical world model might not be correct. In the next few lectures, we'll be studying the methodology of statistical tests. They'll give us a structure to investigate the types of questions that we've illustrated in these examples. And so that we'll be able to conclude, is the difference just due to chance? Or does it contradict an assumption we've made about our theoretical model, so there's some other explanation for the nature of the data?